In this lecture, I'll be reviewing the basics of rate law equations developed from mechanisms or from the mechanisms themselves if we know the rate determining step. So this is an introductory lesson on rate law and rate law equations. So let's get started. So what I have here written already is a elementary reaction. Now an elementary reaction is a reaction that is one step. So it occurs only in one step. Now, what does that mean? Because you may think all reactions occur in one step, and that is not true. Most reactions occur in multi-step functions. What I mean by that is, let's pretend I have the same reaction. And let's pretend this is one step. If this is one step, we would say that the reaction mechanism, which usually means all the steps necessary, okay, is just this single step. But let's pretend there's another proposed way that this could work. Let's say X plus, let's say, a catalyst makes XC, and let's say XC reacts with Y to make XY and reproduce the C. We would call this two-step reaction a mechanism. This is how the reaction that's how the reaction actually occurs. We call it a reaction mechanism. Now, a reaction mechanism is nothing more than a series of steps, and each step, this could be step A and step B, okay? So this is a two-step reaction mechanism. This entire two-step process, I'll draw a line better, this entire two-step process has to overall equal to the overall process. So if we look carefully, we can see what we can cancel. XC is on this side, XC is on this side. The reason why I can cancel is because on either side of an equation, we have the net change. And of course, I'm canceling out C here and C here. And what I'm left, if you noticed, is X plus Y going to XY. So notice I could get to the overall equation by a series of steps, in this case 2, which is called the reaction mechanism, okay? Or I could get to this exact equation in one step, which we'd call an elementary reaction. So if there's multi-steps, I guess a better way to call it, if there's multi-steps, which means there are many steps that have to cancel out to give you the overall, we call it a mechanism. And if it's one step, we call it an elementary reaction. But be careful, understand that each one of these steps amongst themselves is an elementary reaction. So we have two elementary reactions that create this mechanism. Now, the thing is, and the question is, does the reaction occur in one step, or does it occur in this mechanism or another proposed mechanism? See, all we can do is propose what us chemists think of how these reactions occur. And we test to see if the reaction occurs in one step or in a multi-step scenario. That's all we can do. We can't look at a reaction and know, hey, that's one step, or it's multi-step. And I'll tell you, most chemical reactions are made from a reaction mechanism with multiple steps. Could be 10, 15 steps. Many reactions and most reactions have a mechanism, a series of one-step process that gives us the overall. But again, we don't know by looking. We have to test. Now, before we test and figure out whether a reaction does occur in a single step or multiple steps, and you may say, oh, well, why do we care? We care because there's a whole huge million and billion-dollar pharmaceutical companies that love to know exactly how reactions work. And if we know how reactions work exactly, we could hijack a second step or a first step, and we could stop the second step. You say, well, why do we do that? Well, pharmaceuticals make drugs that do different things to our body. What they do is they get into these reaction mechanisms and they make them go faster, slower, stop them, inhibit them, but they have to understand how the whole process works in order to figure out a drug that'll do something in our body. So we really care as chemists how reactions occur. But again, we don't know by looking at an overall chemical reaction. Overall chemical reaction could be one step, elementary, or the sum of many individual steps called a reaction mechanism. So again, we have to figure out that test. Now, before I can talk about the test, we have to go over some basics. Let's pretend for right now that x plus y gives me xy, okay? And let's pretend that it's definitely a one-step mechanism or an elementary reaction. So we're going to pretend it's definitely one step. Now, if it's definitely one step, let's think about this for a second. Let's do a test. And we'll do a test by changing something called the initial concentrations. So let's pretend I have some x's in my reaction vessel and I have some y's. Okay, we're going to keep the y constant, and we're going to see, remember, the whole point of this is to figure out something called a rate law formula, which means how fast something can form. So the reason why we care about this is we're trying to figure out the rate of the reaction, how fast in molarity of this, let's say in this case, the product per second, how fast we make that. So we're going to build an equation at some point that's going to help us figure out how fast the reaction goes. And again, that is separate than trying to figure out how the reaction works. So we're doing, basically, we're killing two birds with one stone. Not that I'm into killing birds or throwing stones, but we're going to build something called a rate law equation that will, number one, help us figure out how the reaction actually occurs, which is important, and two, it'll help me able to figure out, can I actually calculate how fast I make a reaction occur? And you may say, well, why do I care about that? Well, I'll tell you this. If you're building a chemical plant or you're having a product being made, we care how fast we make products. How many molarity per second does it occur? So if you have a reaction that barely goes forward, and we saw a couple examples of that, the hydrogen peroxide demonstration we did, barely went forward until we added a catalyst. So we have to be able to figure out how much of these reactants and how they affect the reaction rate. So that's what we're going to do here. So I have a definite one-step problem. And here's what I'm going to do. Keeping the number of y's constant, I'm going to double the x's. Now, knowing that this is only one step right now, it makes sense that y has to hit x to make xy. There has to be a collision. If I double, okay, times by 2, if I double the number of x's, isn't the x going to find y in twice the speed? And I'll say that again. If I double the number of x's, isn't x going to find y in half as much time? And the answer is yes. We're going to double the reaction rate. It's going to take half as long to make xy because the x's are going to find y twice as fast because there's twice the number of them. So when I double the concentration of x, I double the reaction rate. And in this case, it's doing the same thing. So whatever I do to the initial concentration of x, if I increase it, I increase the reaction rate equally. And in this case, whatever you do to a reaction, a reactant, a concentration, whatever you do to the concentration, initial concentration of reactant, if that change is the same change that the rate has, we call that first order. Now, first order represents this. We would say that the rate of reaction, okay, we're building a chemical formula, or I'm sorry, building a equation that tells us the rate. We would say the rate is equal to some constant, it's like a proportionality constant, times the concentration of x to the first power. Now that first power means first order. Now you should know anything to the first power, if 2 to the 1 is 2, 3 to the 1 is 3. So whatever changes you make in x, it's going to make the same change in r. So if x doubles, right, if 1 becomes 2, because you have the order of 1 here, okay, well, when you go from 1 to 2, you're going to double x, and r is going to equal to the first power, means you're going to double r. Let me explain what I'm talking about. If r equals this k, and let's say it's 1 to the 1 power, let's pretend 1 is k right now, r is going to equal what? 1. Now, if I have R equals K, which is still 1, it's a constant, and now I double the concentration. This is tau to the 1 power. Now R is equal to 2. Whatever number I put in here, because this is to the first power, is this exact number, and because R equals it, it does exactly the same. So I doubled the what? Concentration of my X. I doubled my R. It's doing the exact same. The reasoning, because we have an exponent of 1. Okay, so first order means whatever you do to that reactant, keeping the other one what? Constant, you do what? Do the same thing to the R. All right, so we say it's first order. Now, with respect to Y, we'll do the same thing. If you take all these X's away, let's put back the same number of X's, and the reason why I'm doing that, it's a 1-to-1 stoichiometric ratio. If I double the Y's, and keep X constant, isn't X going to find the Y's twice as fast because there's twice the number of them? And the answer is yes. So if we double the Y's, we'll double the reaction rate because these will collide twice as fast because there's twice as many of them. So this is the same thing. You double this, you double the reaction rate. We're keeping X constant as a control. And we'd write this as Y to the first. So this is also first order. Okay? Now, if you look at this, you'll say, wow, they're both first order. And we would say the total order of the reaction, since they're both first order, when you multiply numbers with exponents, you've learned to add them. So we would say, in this case, the overall order of the reaction is 2. Now, what does that mean? Well, think with me for a second. If I was to double X and I was to double Y, okay? So if I double X and I double Y, now there's 4 times the ability for them to react faster, right? When we had just doubling what? X was going to find Y twice as fast. But if I double Y at the same time, Y is going to find X twice as fast also, which leads us to a reaction rate, if you didn't already guess it, would increase 4 times. There's 4 times the speed. Remember, it was just 2 times when you just doubled 1 and kept 1 constant. But if you double both of the Y's and the X's, they're going to hit each other 4 times faster because there's 4 times the possibility. As you can see, there's 4 groups now, 4 times the possibility. So what does that mean? That's called the square of the change. Second order means the overall reaction is second order, which means the rate is going to do the square of the change. This, okay, is the square of the change. These double. If something doubles, and what is the square of doubling? 4. So that's where the second order comes in. All right, let's continue on. What if I have a reaction like this? Let's get rid of this. Let's make this 2Y, and let's make our reaction equal to, let's do this, 2yx. Actually, that would be y2x, right? So y2x. That's our compound. Now, again, we're assuming that this is an elementary step. This only works. Now, before I do that, I should have realized something, and being bad, so I'll go back to where I was. xy equals x plus y equals xy. If it's an elementary step, notice the coefficients become the exponents. Have to be. Has to be. If it is an elementary step, the coefficients become the exponents. The problem is we don't know normally if they are. So in this case, because it is an elementary step, it makes sense that this would be first order. And the reason why I say it makes sense is because if I need what? Same amount of x to the same amount of y, everything I just talked about will occur. Okay? Now, if you don't quite get that, watch when I change this up. Okay, I have now 2 y's, and this is going to make x, I'll do it like that. So now I have this. Now, if you think, let's clean this all up. And I have my x, And now I have to have what? Twice the number of y's. Whoa. So think with me for a second. If I keep x constant, and now I double the number of y's. Now right now I've got twice the number of y's as x. So right now the y is going to find x pretty fast. But if I double the amount of y's, isn't there really 4 times the opportunity? Right? Although I double the amount of y's, look at this. Isn't there now 4 times the chance of y finding an x faster? And the answer is yes. So the rate is going to increase 4 times when I double this guy, because with respect to y, we would say y is second order. What does that mean? If you double y, right, you increase it from 1 to 2, when you square 2, you get the 4, and the rate is 4 times faster. You see that? If I have to start out with twice as much y, because stoichiometrically that's how it works. So I already have twice as much y, so x is already feeling that. So if I double the y and now have that many more y's, you can see that there are 4 times the number of y's compared to the x now, and now the rate is quadrupled. And the ability for an x to hit a y has increased 4 times. And that's what happens when you say the square of the change. Now, if you had something like this to square the change, let's pretend that this increased 3 times. So if it increased 3 times, if it's the square of the change, the reaction rate will increase 9 times. That's the square. If I increase this 4 times, if it's the square of the change, if it's second order, the reaction rate will increase 16 times. Why? Because 4 squared, or anything squared, is that number there. So that's what second order means. All right? And of course, the coefficients become these exponents if, I'll say if, this is exactly 1 step. The problem is we do not know if it is 1 step. So we have to go and look at experimental data to do so. That's where we're headed. Let's go to that worksheet I gave you to look at some experimental evidence. Okay, I'm back with my worksheet here that is considering the hypothetical reaction. Now it's hypothetical because, well, we don't know if this occurs in 1 step or multiple steps. So what we're going to do is look at the experimental evidence, and we're going to test to see what the rate law is. We're doing this for 2 reasons. One, to get an understanding how this reacts with mechanisms. Is it a 1-step or 2-step, 3 steps? Or we're going to build an equation that I'll be able to solve for how fast the reaction rate goes based on initial concentrations. So let's get started. The rate law, okay, always looks the same. R, which represents how fast, it's molarity per second. That's what this is here. How many molarity per second that C is made. As C is being made, how fast is it being made per second? So R equals a rate law constant. Okay, it's a proportionality constant. All right, it makes the equal sign occur times the concentration of my reactants. Here's A times B. Now you may say, Mr. Grodsky, why don't you just put, because this is a coefficient of 2 here, why don't you just put a 2 here, and this is a 1 in front, 1 here. And the reasoning I can't do that is because I cannot assume it's a 1-step process. I don't know. It's the experiment that's going to tell me what numbers go here. Then I'll see if this is 1 step. If you don't quite get that, we'll get to it. So let's get started. So let's look at the reaction. So we look at the experiment, I mean. So let's look at this. Let's keep A constant. So you notice experiment 1 and 3. Keeping A constant, what happens to B? Now I'm choosing to keep A constant because I just want to look at how B affects the rate without A getting involved. So I have a control here. So if you notice something, B doubled while A stayed the same. What happened to the rate? This is the rate of reaction, the speed of making C. We went from 7.5 times 10 to the negative 5 to 2.8 times 10 to the negative 4. Now for those that don't see this, 2.8 times 10 to the negative 4 is the same as 28 times 10 to the negative 5. So we went from 7 times 10 to the negative 5 to 28. You don't see that. That's an increase of 4 times. So the speed increased 4 times when I doubled b, keeping a constant. Wait a minute, isn't 4 the result of squaring 2? Yes, this is the square of the change. So this is second order. If this increased 3 times and this increased 9 times, that would still be the square of the change, right? Because 3 squared equals 9. In this case, we have 2 squared. And if I had a 4, if this was a quadruple increase, this would increase 9 times. Okay? So that's how that works. Now, of course, you could have a cube. You could have a 3. What would that look like? All right, well, let's say you had this doubled and this increased 8 times. What's 2 cubed? An 8 times increase. So if this increased 8 times and this doubled, that would be a 3 order. Okay, but of course this time, according to the data we have, it's second order. 4 is the square of 2. It's the square of the change. So they put a 2 there. We're almost done. Now let's go to the other piece of data. Let's go going from 2 to 1. 2 to 1, you can see here I'm doubling A. I'm keeping B constant right now because I want to just see what A does without B getting involved. It's the control now. So doubling A, and I picked 1 and 2 because I saw it's doubling while B is staying the same. And I noticed it stayed the same. Look at that. It stayed the same. Doubling A had no effect on the reaction rate, which means it has no effect. That is not a first order. If A was first order, if you remember from what we talked about, whatever you did to A, you did exactly to the rate. So if you doubled A, 2 to the 1 is you double the rate. So it's not one order. We would call this zero order. Now, why zero order? Well, something to the zero order, anything to the 0 power is 1. So what happens is, because this had no effect whatsoever, we get a 0. Now, what does this mean? A to the 0 power, this whole thing equals 1, which means, because it has no effect, the rate equation could be written like this. It's okay to write it this way, but R equals K. I can put a 1 here, but, you know, what's the point? B squared. And there it is. There's my rate law equation. It's that simple. But I had to figure out what? I had to figure out these exponents based on what? The experiment, not the coefficients. Look at this for a second. The coefficients are 2 here. So this worked out fine. This is a 2 here, this is a 2 here, but there's a 1 in front of the A. There's a 0. So what does this mean? Think with me for a second. Did we prove in this experiment that this was a one-step equation? We did not. The coefficients do not match the exponents, which means this does not occur in one step. This occurs in multiple steps. Has to. And I'm going to explain that after I finish the rest of this, which is very, very basic, very, very important that we do. So let's do that. Letter B. What is the order with respect to A? A would be 0. It had no effect. With respect to B, it's 2. It's a square of the change. You square what you do here, that's what the rate becomes. So the orders are the exponents. Okay? What's the overall rate order? You add the exponents together, so 2 plus 0 is 2. Okay, next question. What is the numerical value for the rate law constant? How do I do that? Well, I know the rate law is R equals K, and this is B second order. A is to the 0, it's 1, it's there, but you don't have to need that value. Now, because K is a proportionality constant that we need, it helps us make a proportion into an equal sign. When we explain the universal gas constant, it's the same kind of deal. Okay, we've got to pick an experiment. So I'll be crazy and I'll pick number 1. In number 1 experiment, I had a rate of 7.0 times 10 to the negative 5. It's equal to K, which we don't know. And what's the value of B? 0.1, and of course it's squared. And we solve for k. K is equal to 7.0 times 10 to the negative 5. And look at this. We square 0.10, and we put the values in. You do your math. 7.0 times 10 to the negative 5 divided by 0.1 squared, you get 0.007. That's an important number. However, we need to have our appropriate units. Let's think what we have here. Rate, this R, is in what? Molarity per second. How much stuff you have per second. This bracket is a concentration. It's got molarities in it. So it's molarity squared because you're squaring it. So how can we simplify these units? Well, molarity over molarity squared means we're going to take this molarity away and this becomes 1. And this S is really the denominator in the numerator is the denominator. So this, okay, will work out itself to be 1 over second and 1 over m. And there's a nice way, a big boy, big girl way to write this. We would say s to the negative 1, m to the negative 1, which means exactly this right here. So the answer should be written 0.007. I'll do m first, and s to the negative 1, which is the same thing as saying 1 over m to the second. Either way, you have to make sure your units are correct. It's a big point here. Now, if you had a different order of your reaction, your units will be different. Don't fall in love with the idea that these units will always be the same. Okay? So because if you had a, if the x was, if you had an a here that was 1, this would be cubed, and you could see that there'd be different number of m's there. So you got to pay particular attention to those units. Now, so we've got the value of the constant. All right, we have everything done. Now the last question, and really a powerful question, what is the rate when A equals this and B equals that? You notice these aren't the values in the experiment at all. These are arbitrary values, but they're not that arbitrary. Once I have the K, guys, once I have everything I need for my rate constant, I can solve for the rate. Think with me for a second. Knowing the rate law equation, which equals K times A to the 0 times B squared, once I have the value of K, guys, I can solve for the rate that I need to keep the factory going. So we said I need to be making a certain product at a certain speed, okay, at a certain temperature. What must be the concentration of the reactants to keep it going? So this is a very important equation. So you solve for it. So what is my R? It equals A to the 0 is 1, so I don't use this. B squared, so 0.050 squared. And of course it's times K, which is equal to 0.007. That's 1 over M and S. And of course this is, I forgot the unit here, Bad Grodsky. So this unit of course is molarity, and that's squared. And that's going to equal the rate. Now the rate should equal a molarity per second. So you notice this is molarity squared. So when you have molarity squared over 1 over, or I should say just 1 over m to the s, what do you have? Well, this goes bye-bye. You have 1m, you have m over s left, which is the unit of molarity per second. So we put this in our calculator and let's get a number. So if this is my initial concentration, what I get is a rate is equal to 1.75 times 10 to the 5 to the negative 5. And the units is molarity per second. So I can solve for how fast something's going to go based on initial concentrations now that I have my K. Okay? Now we're going to just talk about for a second the implications of this 0 in terms of how this reaction occurs. Yes, one thing we just did is found the rate law, and we're able now to solve for any concentration of my reactants. Knowing our rate law constant now that we just solved for, we can figure out how fast our reaction will go. And that's important in industry, very important. We have to make sure we're keeping our rate high enough so that we can make some money. Therefore, we should know exactly how much reactants we have to have in the reaction vessel. Very important. So now we're going to talk about what does it mean. This occur, like I said before, does not occur in one step because the coefficients do not match the rate law. Something else is occurring. We have something called a mechanism. And I'm going to discuss that right now. Okay, so as we look at our coefficients, we know that the rate law here is 0 for A and a 2 for B. So the orders here were 2 for B, which makes sense here. There's a 2 in front. Okay, that didn't work out. And there's a 0 for A. So the coefficients, which is a 1 here, do not match the orders. So clearly this is not an elementary step, because if this was a single elementary step, if I doubled A and kept B constant, B would hit A twice as much, and the rate should go up twice as much. But as we can see from the experiment, A did not change. When you kept B constant, when you kept B constant and A doubled, the reaction stayed the same. So we say A is a 0 power, which means it's 0 order, which means that A, okay, was not involved with the slowest step. What do I mean by that? Well, let's pretend that A plus 2B makes B2A. I'm going to change C to make things simple. What I mean by that is, let's go write us a proposed mechanism. It can't be one step because the coefficients aren't matching these exponents from the experimental data. So it's implying that we have a mechanism with individual steps. So I'm going to propose a mechanism. I'm going to say, all right, 2B's plus C, could be some catalyst, equals B2C. B2C would be the second step, or the second reaction, plus A gives me B2A plus C. And this is the first step, and this could be the second step. This is a proposed mechanism. This is what we do. And if you notice, if I cancel, this C cancels, B2C cancels, and I'm left with 2B plus A to B2A. So it's the same reaction that we overall get by a couple of steps. Because the coefficients did not match the exponents in the rate law, it did not occur in one step, it occurred in multiple steps. We call this, of course, a mechanism. And this mechanism is a series of elementary steps. Now, if you look with me carefully, this is a catalyst. Catalysts start a series of steps, and as you know, catalysts do not get what? Do not get used up in a reaction. So this catalyst started this series of steps and was reproduced. So I know the catalyst is this. This right here is an intermediate. It was produced and then it's used up really fast. Catalysts and intermediates are not in the rate law because they're not the initial reactants, and the intermediates are not around long enough. Usually intermediates are so reactive that they react immediately as soon as they're made. So that means as soon as this is made, this reacts fast, which means the first step is probably the slowest step. The second step is waiting for the second step to. All right, so I'm going to say the slowest step is number 1, and we call the slowest step, or the step that is the slowest, the rate determining step. Why? Well, we're going to say this first step was slow, and the second step is fast, because we're making what? A reactive product that's quickly going to go. So the second step is fast. Well, this whole process of making B2A is dependent upon the slow step or the fast step. Well, we're as fast as our slowest step, right? Trying to get out of the house during the day, and my wife, okay, me and my family want to go somewhere, my wife's a little bit slower to get ready. I can only go as fast as my wife gets out of the house, okay? And I love her, but it takes a little while. So my friends in chemistry, we're only as fast as our slowest step. So my friends in chemistry, this step right here determines the rate law. And because it is a single step, the rate law depends on this. So notice, there is no A in the slowest step. That's why there's an A0. And A0 says to me that there is no A in the slowest step. Look at this. There's a 2 in front of the B. Yes? There's a 2 here, which means there's a 2 here. What I'm trying to tell you guys is that the information that this experiment gave me helped me understand that this reaction could occur in a multi-step process, whereas the A, one of the reactants, is not in the slowest step. The slowest step is an elementary step. This is an elementary step. And as I told you, the elementary step will give you the coefficients. Because A isn't in this step, it's a 0. Because there's a 2 in this one step that depends on the rate, because you're depending on the slowest step, you get a 2 here. All right? Now, let's look at some more mechanisms. Let's go on to the back sheet, flip it over 9 times, and we've got this overall reaction. And I ask you, what is the overall process? Well, I've got an I on this side, an I on this side. They cancel. I've got an iodate on this side and an iodate on this side. They cancel. What's left over? 2 H2O2s, which is hydrogen peroxides, makes 2 waters plus an O2. That's the overall reaction. Now, when they said predict the rate, I'm going to look how fast the reaction occurs. And I see that this is the slowest step. The slowest step is the what? The rate determining step. We are only as fast as our slowest step. So the rate law, which is equal to K times the concentration of what is in my slowest step. So this is my what? Slowest step. This is my elementary step, right? This is the elementary step. And what do we know? In the elementary step, the coefficients become the exponents, right? If this is the slowest step, this is the step that determines the rate law. And there's a coefficient of 1, and I put that there. The other step is needed for the overall process to occur, but the rate doesn't depend on the fast step. It depends on what? Waiting for the slowest step. We are as fast as my slowest step, so the rate law depends upon this elementary step, so the coefficients become exponents. Notice in the reaction there's 2 H2O2s. There's only 1 in this rate law, because in this reaction only one of the H2O2s is in the what? Slowest step. Okay? And we could say the other H2O2 is a 0. It's not there. This H2O2 is not in the slowest step, so it's not part of the rate law. However, I will say you still need to what? Have it in order for the reaction to go. But the reaction rate, how fast we go, does not depend upon that second one. Okay? Identify the intermediates. Well, intermediates, guys, are the elements that what? Link the one step to the other. So the iodate ion is an intermediate, very highly reactive. That's your intermediate. It links one step to another. What do you think my I negative is? My I negative, okay, is my catalyst. All right, that's my catalyst. Why do I know? Because I know it starts the process and it gets reproduced. Notice the iodate does not. So how do you distinguish between an intermediate? Intermediates link one step or one elementary reaction to another. What does a catalyst do? It starts the series of reactions, starts the mechanism. And you can see that it's in the reactant side and then it gets reproduced. One more point I want to make, this was an exothermic process that barely went. When I put the hydrogen peroxide out, it was decomposing. But it needed 2 of these to collide, and the activation energy was too high. By adding an iodide catalyst to the reaction, what I did is I started a series of what? Two reactions that were collectively lower in energy, so I lowered the activation energy by doing the two steps. Here's the first step, the little hump, and the second step. I don't know if it's exo or endo, I'm just writing them to show you that we changed the pathway. People like to say that catalysts lower the activation energy. They do so because the series of steps that they do change the overall pathway. The overall cost to start the reaction is lower, and the reaction proceeds faster. But a catalyst starts the exact mechanism, starts this pathway. Without this I negative, it doesn't occur. All right, so try the rest of this ditto, look on to the key. I hope that was a great introduction for you.